Hadean Eon. The Hadean is the first and oldest of the four geologic eons of Earth's history, starting with the planet's formation about 4.6 giganom, estimated 4,567.30 plus or minus 0.16 megaannum, set by the age of the oldest solid material in the solar system, protoplanetary disk dust particles found as chondrules and calcium, aluminium-rich inclusions in some meteorites about 4.567 giganom, and ending 4.031 giganom. The age of the oldest known intact rock formations on Earth is recognized by the International Commission on Stratigraphy.
The interplanetary collision that created the Moon occurred early in this eon. The Hadean Eon was succeeded by the Archean Eon, with the late heavy bombardment hypothesized to have occurred at the Hadean-Archean boundary. A sizable quantity of water would have been in the material that formed Earth. Water molecules would have escaped Earth's gravity more easily when the planet was less massive during its formation. Photodissociation by shortwave ultraviolet in sunlight could split surface water molecules into oxygen and hydrogen, the former of which would readily react to form compounds in the then reducing atmosphere, while the latter, along with the similarly light helium, would be expected to continually leave the atmosphere, as it does to the present day, due to atmospheric escape.
Part of the ancient planet is theorized to have been disrupted by the impact that created the Moon, which should have caused the melting of one or two large regions of Earth. Earth's present composition suggests that there was not complete remelting, as it is difficult to completely melt and mix huge rock masses.
However, a fair fraction of material should have been vaporized by this impact. The material would have condensed within 2,000 years. The initial magma ocean solidified within 5 million years, leaving behind hot volatiles which probably resulted in a heavy CO2 atmosphere with hydrogen and water vapor. The initial heavy atmosphere had a surface temperature of 230 degrees Celsius (446 degrees Fahrenheit) and an atmospheric pressure of above 27 standard atmospheres.
Studies of zircons have found that liquid water may have existed between 4.0 and 4.4 Ga, very soon after the formation of Earth. Liquid water oceans existed despite the high surface temperature, because at an atmospheric pressure of 27 atmospheres, water remains liquid.
The most likely source of the water in the Hadean Ocean was outgassing from the Earth's mantle. Bombardment origin of a substantial amount of water is unlikely, due to the incompatibility of isotope fractions between the Earth and comets.
Asteroid impacts during the Hadean and into the Archean would have periodically disrupted the ocean. The geological record from 3.2 Ga contains evidence of multiple impacts of objects up to 100 kilometers, 62 miles, in diameter. Each such impact would have boiled off up to 100 meters, 330 feet, of a global ocean, and temporarily raised the atmospheric temperature to 500 degrees Celsius (932 degrees Fahrenheit).
However, the frequency of meteorite impacts is still under study. The Earth may have gone through long periods when liquid oceans and life were possible.
The liquid water would absorb the carbon dioxide in the early atmosphere. This would not be enough by itself to substantially reduce the amount of CO2.
A 2008 study of zircons found that Australian Hadean rock contains minerals pointing to the existence of plate tectonics as early as 4 giganom, approximately 600 million years after Earth's formation. However, some geologists suggest that the zircons could have been formed by meteorite impacts. The direct evidence of Hadean geology from zircons is limited, because the zircons are largely gathered in one locality in Australia. Geophysical models are under-constrained, but can paint a general picture of the state of Earth in the Hadean.
Mantle convection in the Hadean was likely vigorous, due to lower viscosity. The lower viscosity was due to the high levels of radiogenic heat and the fact that water in the mantle had not yet fully outgassed. Whether the vigorous convection led to plate tectonics in the Hadean or was confined under a rigid lid is still a matter of debate. The presence of Hadean oceans is thought to have triggered plate tectonics.
Subduction due to plate tectonics would have removed carbonate from the early oceans, contributing to the removal of the CO2-rich early atmosphere. Removal of this early atmosphere is evidence of Hadean plate tectonics.
If plate tectonics occurred in the Hadean, it would have formed continental crust. Different models predict different amounts of continental crust during the Hadean. The work of Diam et al. Predicts that by the end of the Hadean, the continental crust had only 25% of today's area. The models of Karenga et al. Predict that the continental crust grew to present-day volume sometime between 4.2 and 4.0 giganum.
The amount of exposed land in the Hadean is only loosely dependent on the amount of continental crust, it also depends on the ocean level. In models where plate tectonics started in the Archean, Earth has a global ocean in the Hadean. The high heat of the mantle may have made it difficult to support high elevations in the Hadean. If continents did form in the Hadean, their growth competed with outgassing of water from the mantle. Continents may have appeared in the mid-Hadean, and then disappeared under a thick ocean by the end of the Hadean. The limited amount of land has implications for the origin of life.
Abundant Hadean-like geothermal microenvironments were shown by Soldat et al. To have the potential to support the synthesis and replication of RNA and thus possibly the evolution of a primitive life form. Porous rock systems comprising heated air-water interfaces were shown to allow ribozyme-catalyzed RNA replication of sense and antisense strands followed by subsequent strand dissociation, thus enabling combined synthesis, release and folding of active ribozymes. A study published in 2024 inferred the last common ancestor of all current life to have emerged during the Hadean, between 4.09 and 4.33 giganum.
Although the early part of the late heavy bombardment happened during the Hadean, the impacts were frequent only on a cosmic scale, with thousands or even millions of years between each event. As Earth already had oceans, life would have been possible, but vulnerable to extinction events caused by those impacts. The risk would not be on the frequency, but on the size of the impactor, and remains on the Moon suggest impactors bigger than the Chicxulub impactor that caused the extinction of dinosaurs.
The Hadean Eon can be, hypothetically, divided into two eras: Paleo-Hadean era, 4,567.3 to 4,404 million years ago, include Hyperition period, 4,567.3 to 4,560 million years ago, Titanomachy period, 4,560 to 4,450 million years ago, and Hephaestion period, 4,450 to 4,404 million years ago, and Neo-Hadean era, 4,404 to 4,031 million years ago, include Jacobian period, 4,404 to 4,280 million years ago, Canadian period, 4,280 to 4,200 million years ago, and Procrustean period, 4,200 to 4,031 million years ago.